Building robots that learn from trial and error. I'm Tonya Hall, and joining me is Dr. Dmitry Berenson, Associate Professor in the Electrical Engineering, Computer Science, and Robotics Institute in the College of Engineering at the University of Michigan. Welcome, Dr. Berenson.
Thank you. It's great to be here.
Give us a brief summary of your background related to robotics.
Yeah, so I've been involved in robotics ever since I graduated from undergrad, even during undergrad. I've been working on all kinds of different robots, from legged robots to helicopters to robot arms to humanoid robots. Um, and my kind of area of expertise is in motion planning and learning for robotics and motion planning. So I create algorithms that enable robots to do tasks like cleaning up a table, doing the laundry, and even exploring some tasks in healthcare, surgical robotics, and things like that.
Let's talk about building robots that learn from trial and error. What are the building blocks of such a system?
Well, there are a lot of different systems out there for doing this, but one mode that's become really popular recently is to use deep learning. So you use neural networks with many hidden layers to process usually some high dimensional data, like images or point clouds. And that data is then turned into motor commands for the robot. So this is one very popular paradigm that's been developed recently. And it's only become possible because we've had a huge amount of computation that we can throw at the problem. But unfortunately, this method is somewhat limited because it's very task specific. So you learn, let's say, a way to take in images and produce motor commands for, let's say, cleaning up a table, which is already pretty hard. But it turns out if you want to do a slightly different task, like maybe you clean up a cupboard where the lighting conditions are different or the kinds of objects you're encountering are a little bit different. Well, in that case, it's actually very difficult to transfer any of what you've learned from cleaning up a table to the cupboard. Now, maybe there's a little bit that can transfer, but usually you're going to require a whole new set of training data. You're going to have to retune your architecture, which is the structure of those deep networks. And basically, you're going to have to do a lot of engineering work to enable that new application. So while these kinds of learning methods are actually very impressive and a great development for the field, there's still actually a long way to go before we are able to fluently understand what we can actually learn that's transferable across a broad range of tasks.
What role does machine vision play in all this?
So machine vision is very important, and in the robotics world, we traditionally built systems that took in some uh, estimate of the robot state and the state of the environment, which came from a machine vision system. So you would have algorithms, for instance, implemented in OpenCV or other vision frameworks that could, let's say, track features in a scene so that the robot could estimate its location relative to those features. You could have machine vision that recognized objects. So for instance, if I'm cleaning up the cups from the table, I want to be able to recognize what's a cup and what's a plate and what's a fork and so on. So that was the traditional system where we're using these kind of pre-made machine vision algorithms. Maybe we're training them on a small data set, and then we are able to recognize objects or recognize features in the scene. And then we can go on and use those in motion planning, localization, all sorts of different things we want to do in robotics. But now the paradigm has changed somewhat, and people are seeing that kind of isolating vision from the rest of the system completely is maybe not the right way to go. Maybe some contexts you can do that, But in other contexts, the actual states that you want to estimate for what's going on in the world are intimately tied with what you're trying to do in the world. So you can't kind of decouple these systems and say, well, you make a perception system and I make a motion planning system or a localization system. Now, that's actually pretty advanced work to actually do it together. And a lot of these neural network approaches are trying to do this kind of stuff together. I'm actually of the opinion that what we need is something in the middle. We don't want to completely isolate our perception from our application that we're using it for, but nor do we want to kind of learn everything at the same time, because then we're kind of starting from scratch. It's like a new baby being born and it's got to figure out how to move its body and how to use its eyes every time it wants to do something, right? That's not feasible. So I think there are common perception things that we can learn and common perceptual features that we can extract from the scene, but we may need to do another extra layer of learning a little bit after that so that we extract from that large set of features what's actually relevant for the task that we want to do.
What goes into designing the trials and errors to create a robot that can actually perform a wide variety of situations?
Yeah, so a lot of trial and error these days is done in simulation. So the idea is that you have a simulator, which is just a program that you run on your computer that simulates, let's say, physics. Again, we're talking about a robotics context here. So we have a physics simulator, and that simulator has been kind of set up with a certain model of the world. So imagine, again, cleaning up a table, right? Maybe I create a table in simulation and I put some cups and plates and forks on it, right? And given the simulator's physics, I can figure out what happens if the robot, let's say, pushes one of the cups or it picks up a plate, right? Maybe that plate will knock over a fork. Maybe it'll knock over a cup. Maybe nothing will happen except the plate moves, right? So the simulator can basically tell us what the results of our actions are, right? So once I know that, then I can try many, many different actions in simulation. I can run this in parallel because I can run multiple copies of the simulator, maybe in different worlds, meaning that they have different physics involving, different kinds of friction, different kinds of masses for the objects and so on. And so I can do all of these different runs in parallel, and I can get an estimate of how robust a given action is to changes in my world, right? And that can allow me to search for actions which are much more robust. So that's kind of the crux of using trial and error. But there's a layer on top of that, which is basically looking at how do we perceive the state of the environment in simulation, and then come up with the best action to do using, again, a lot of these deep learning methods. You could also do it with more traditional methods. That layer is basically synthesizing the actions to test. It's looking at what the result of the action is, and it's using that as feedback to then improve its model for how to perceive and how to act. So that's the simulation side of the story. But of course, making a robot that only works in simulation is not that exciting, right? We want robots to do things in the real world. So what that means, to accomplish that, what we need to do is actually transfer what we've learned from simulation to the real world. This is called sim to real in the robot learning community. In the real world, we can gather some data and we can kind of refine our simulation models and fine tune them for the real world application. Now, what transferring from simulation to reality is actually not a trivial thing, because the physics inside the simulator and the way things look inside the simulator aren't the same as the real world. And so you always have what's called the reality gap. The reality gap is basically the difference between the simulation world and the real world. And right now, there's a lot of research going on about how to best cross that reality gap by doing different kinds of sim to real transfer methods.
Dr. Dmitry Berenson, Associate Professor at the Electrical Engineering, Computer Science, and Robotics Institute in the College of Engineering at the University of Michigan. If somebody wants to connect with you, maybe they want to find out more about this area of robotics, how can they do that?
The best way is just to send me an email. So you can find my website just by Googling my name, or you can just email me at berenson@eecs.umich.edu.
Sounds good. Thanks again for joining us. And if you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.